Hi everyone. So I almost forgot that I didn't upload the second part of the chapter 8. I tried to record it a couple times and it just hadn't worked out. So I will upload this now and then we will all talk tomorrow at 3 p.m. Okay, so the last part of this half of chapter 8 is going to go into covalent bonding. So the first part was talking about ionic bonding, and that's where you have that magnetic force, right? You have a cation and you have an anion, and they create this ionic electrostatic force that connects them, that draws them towards each other. Now, covalent bonding, as we know, which is two nonmetals, which are both anions, those they don't automatically have that magnetic attraction, right? So how are they actually held together? Well, they actually share their electrons. So instead of actually taking an electron or giving an electron away, they actually both share their electrons to create one bond. And so that's kind of what we'll be talking about when we talk about covalent bonding. Okay. So, what is the nature of the bonding in molecular compounds? Recall the octet rule, the tendency of an atom to achieve an electron configuration having 8 valence electrons. Covalently bonded atoms achieve 8 valence electrons by sharing electrons between them. Okay, in this example that you see on the board, hopefully you guys will be following along, right, while I'm going over this. So here, each hydrogen atom, as you can see, it's saying it has one electron, right? And so remember when we discussed going over the different valence electrons, right? We said that you can look at the periodic table and see that you have a certain amount of electrons, right? So you have a 1, this is 1A, or this is group 1, and so all of these are going to have 1 valence electron. All of these are going to have 2 valence electrons. And there's 3 valence electrons, 4, 5, 6, 7, 8, right? So remember that. So here you show that we have 2 electrons, right? And, well, 1 electron per each hydrogen in the 1 s orbital. So you have these 2 hydrogen molecules, or 2 hydrogen atoms, right? And they come together to form a hydrogen molecule, which would be H2, right? So when these 2 come together, first they're by themselves, they come together and they kind of share these electrons. So one kind of comes to the top and the other one kind of comes to the bottom. And they both share this electrons in order to create a bond. So instead of giving one gives it its electron and the other takes it, they just share it. So another example here is looking at these chlorine atoms. So in there's 2 3p orbitals. So that's just saying that this is in the 3p orbital shells, the valence electrons for chlorine. And these last electrons that are on the outside. Each one, these are both chlorine atoms, they come together and they share their electrons, and that's how they create a bond. So they just kind of literally, if you kind of think about one is kind of coming to the top and the other one's coming to the bottom, they kind of just share this space. And now that they're in this space, they create kind of this molecule around those 2 shared atoms. Okay, so you have different levels of bonding. We are going to talk about all 3 of them. So there's 3 types of bonds that you can have. You have single covalent bonding, double covalent bonding, and triple covalent bonding, and that's it. You cannot have quadruple covalent bonding. Okay, it's just straight 1, 2, 3, single, double, and triple. Okay, so now we just are going to go through and break each type of bonding down. So what is single covalent bonding? A covalent bond that consists of a pair of electrons shared by 2 atoms. So as we saw in those examples earlier, right, with the hydrogen and chlorine, each one had 1 electron and they came together to share a new molecule, but they came together and shared their electrons in order to create a new molecule. So that would be a pair of electrons, right? Because it's 1 electron from in this case, 1 electron from the fluorine, 1 electron from the carbon. And each electron, so if fluorine has an electron and chlorine has an electron, carbon has an electron, they come together and they form this one bond. So that's considered a single covalent bond. So it's a bond that consists of a pair of electrons shared by two different atoms. So the atoms are fluorine and carbon, and then each one is sharing one electron. The orbitals overlap, as you can see, to allow the electron pair to be located around both atoms. So that's how they share. So instead of them actually giving an electron or taking an electron where they maintain their own space, here they actually will overlap. And so in that overlapping, that area, they're sharing. So when you have a pair of electrons, that's a single bond. So multicovalent bonding. So these are bonds that consist of more than one pair of electrons shared by two atoms. So you have double bonds and you have triple bonds. So with a single covalent bond, we said that you need a pair of electrons, right, between two atoms. So here is a pair of electrons, right, these two dots here. That's a pair of electrons between two oxygen atoms. So that's a single covalent bond. But then you move down, you realize there's two more pair. So it's another pair of electrons between two molecules. So because there's two pairs of two electrons between two molecules, that's considered a double bond. So it's like one pair is one bond, and then the second pair is another bond, and that's double bond. So same thing with the nitrogen. So here you have the two electrons that are being shared, two electrons that are being shared, two electrons that are being shared. So because there are 6 electrons that are being shared between the two nitrogens, that means there's 3 bonds that are here. So because there's 3, so you have 1, 2 here, and 1, 2, 3 here, because there's 3 pairs of electrons here, so triple bond, and 2 pairs of electrons there, so double bond. Okay? Hopefully that all makes sense. Okay, so just more kind of details with the multiple bonds. Remember atoms bond in order to gain an octet rule, right? And we remember the octet rule, so every single atom wants to be super stable, right? They want to be noble, and that's them satisfying the octet rule, which means that they're going to have a total of 8 electrons surrounding that atom, right? So just remember that as well when we're going forward into drawing these structures. Each atom that you're looking at should always have at least 8 electrons around it, because that's the whole point of it sharing with another atom, okay? So, in order to do this, atoms can also share more than one pair of electrons, up to a maximum of 3 pairs. So this is just kind of a review of what we just were talking about. You have sharing 1 pair of electrons forms a single bond. Sharing 2 pairs of electrons forms a double bond. Sharing 3 pairs of electrons forms a triple bond. And once again, as I've said before, there are no quadruple bonds. There's just single, double, and triple. That's it. 1, 2, 3. You don't go past the A, B, C's, 1, 2, 3's, right? Okay, let's keep going. Okay, actually, I'm going to go through this slide first and then the next one. Okay, so earlier we discussed going over the Lewis dot structure, right? So we have the Lewis dot structure and then we have the Lewis structure. The Lewis dot structure is specifically telling you that you're going to be drawing using dots, right? So when we had like the rubidium, we had a dot, right? Remember? And so that means they want us to represent the structure of the valence electrons or the electrons or the compound using dots, right? So if it says you want the Lewis dot structure, that will be something well, let's add this hydrogen onto here. All right, this would be an example of a Lewis dot structure. And this would be an example of a Lewis structure, is when you have the line. Okay, so the dot structure is where you have dots, and the line structure is where you just basically don't have dots. So if it says Lewis dot structure, you have dots. If it's the Lewis structure, then you just have lines, okay? Okay, so in learning about the covalent bonds, we have to figure out how do these bonds share electrons, and how do we actually write these things out, right? Like, how do we actually put them on paper and draw what the structure really looks like? How do we interpret that? And so we interpret that by using these line structures to say, oh, this is what this molecule is. So we've gone through the names of different compounds, and so looking now, what we're saying is we're going to take that compound that we've learned how to name and then actually kind of almost unfold it, right? We're kind of unfolding it and putting the arms and the bonds and structures in the specific orientation in which they actually would appear in the molecule themselves. Okay, so that's kind of the purpose of the Lewis structure. So in writing the Lewis structure, these are the most important rules that you want to make sure that you understand. So writing Lewis formula of a compound. So first you want to write atoms in an appropriate arrangement, which means you draw a simple skeleton with the central atom and other substituents attached to it. Okay, so commonly we're going to go over some common like hints and tricks after this, but generally with your central atom, for instance, if you see carbon, like if you see CO, right, or let's see, CO2. Generally, when you see carbon in a molecule, it's going to be like the center atom. And the atom that is the most electronegative is also going to be the center atom. Or the least electronegative. Okay. But we'll review that, kind of go more into that when we go over the tips and tricks. Okay. All right. So, yes. So first, let's just use CO2, just because. Okay. So, and then let's use this as an example to go through each step. So first, you want to pick your central atom. So when, like I said, it's carbon. When carbon's in a compound, it's generally the central atom. So we want to draw the skeleton structure. So the skeleton structure just means like, okay, well, if I have two lines, or if I have two things that are attached to my center atom, I want them, first of all, when you're drawing these things, you want them to be symmetrical. Okay, so you want them, so here you would have oxygen and oxygen, right? So you want them to be straight across from each other, right? So if you had more than that, let's say if it was CO4, you needed 4 oxygens, you would want them to be across from each other. Or if you had 3, you would want them to still be kind of in this perpendicular shape, right? So you're always going to just have these 4 planes that they're going to be drawn on, just an FYI. So when it says draw the skeletal structure, that's what you would be drawing. You say to yourself, you look at the compound and say, well, which one should I pick as a center carbon or as a center atom? So carbon is the generally so carbon, our center atom for these compounds. Let's do CO2. So I would guess that this is how this would look, right? Because I have 1 carbon and I have 2 oxygens. And you want to have them as far away as possible. And that's the best way to write the oxygens, right? As far away as possible. So that would be my first step. And then the second step is to find the number of total valence electrons that are available. So remember how we used the system of being able to look at the periodic table, right, in order to find the valence electrons for certain atoms. So when you have CO2 or any type of compound, you basically are going to take each one. It's almost like it's very similar to finding the I am a loss for words. Finding the molar mass, right? You just add things up together, like the different atoms. You kind of just add them together. So you're going to kind of think of the same thing in terms of the valence electrons. So you would just go look. So we have carbon and oxygen. So first you would look on here and say, okay, what row is carbon in? Carbon is here, and that is the fourth column, right? So I know carbon is 4, has 4 valence electrons, and let's see where oxygen is. Okay, oxygen has 6 valence electrons, okay? So we have carbon has 4 and oxygen valence electrons. And oxygen has 6 valence electrons, but they're 2 oxygens, right? So I'm going to have to multiply that 6 by 2. So then my total valence electrons is, so we have 12, 16. Okay, 16 valence electrons, right? Okay. So then the next thing that you would want to do is you want to find the number of total valence electrons wanted. So now 3 and 4 are kind of hand in hand, because in order to find the total number of valence electrons wanted, you have to do this by finding the number of electrons shared. But what it says by minusing 3 from 2. So basically, what you want to do, the next step that you would want to do, is count the number of electrons that are in the bonds for your skeletal structure. So remember that I said when you have these covalent bonds, what are we talking about? They're sharing 2 electrons. So this is, in a sense, what you're really seeing is, right? Because they're sharing electrons. Okay. So here there's 2 electrons in this bond, and there's 2 electrons in this bond, right? So how many electrons are in our skeleton? How many electrons are currently bonded in our skeletal structure? There's 2 here, right, and 2 here. So there's 4 electrons total. 4 bonded electrons. So you would have four bonded electrons, right? So now what you want to do is in order to see how many kind of free lone electrons that we have, is what we call them, or lone pairs, if there's like more than one that can make a pair, we have to subtract the amount of bonded electrons from the total amount of valence electrons, because these bonded electrons are part of these valence electrons, right? But we already know there has to be 2 bonds, i.e. 4 electrons used to create this structure, because there's 2 substituents, and substituents are just things that are attached to the center atom. So because there's 2, we know that there's 4, right? 4 that are already bonded that have to automatically be a part of this compound. So what you're going to do is you're going to subtract You're going to take the total number of valence electrons minus number bonded electrons. Lone electrons. Okay, so that's, hopefully you can see this. Okay. Hopefully you can see that. So what I wrote was lone electrons equals the total number of valence electrons minus the number of bonded electrons, right? So, because we want to see how many are now going to be kind of a part of, just not necessarily in a bond, but may possibly create a bond, but are not in our skeletal structure, basically, right? So if that means we're going to do 16 minus 4. So then we have 12 lone electron pairs. Okay? So now we have 12 lone pairs. So what you want to do, and I'll write this back at the top so you... Okay, I'm going to put 4. So I'm numbering these, and I know that the my numbering is not going to match this exactly, but just you want to think that the 3 and 4 here is this number 3, okay? And so I'll just, you know what, how about I just make it 3 and 4. Okay, and now this is number 5. Okay, so number 5. So distribute the electrons, the shared electrons between the atoms, right? So you basically, what you want to do is rewrite the structure, and then you want to do of the skeleton structure, and then you want to add all of the electrons that are the unshared, so the remaining unshared electrons. So this is our skeletal structure, right? So I said we have 12 lone electrons, right? Unshared electrons. So what you want to do is, so the whole point of them now coming together and having a bond is that each one of them, you want them to every single atom to be able to fill their octet role. So when you're looking at adding these electrons and creating bonds, at the end, you're going to be looking at each individual atom. Like, does this have 8 electrons around? Does oxygen? Does carbon have 8 electrons around it? Right? So every single atom itself, you want to make sure that each one has 8 electrons. Okay. So, carbon, oxygen. All right. So, when you first start drawing, you're drawing your electrons onto your atoms. So what we're basically doing, if you kind of think about it in the sense we're adding the dots, right, just like we did in the dot structures, to this whole molecule. And then from there, we can see if we can actually create bonds using those pairs. But when you start this, you're going to add your electrons to the outside atoms and then finish with the inside. So I have 12. So I would say I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? Okay, so okay. Oh, yes, that's even better, right? So now you can see the electrons. Okay, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So I have now put 12, I've put all of my lone unshared electrons onto my molecule. So now what you want to do is say to yourself, well, does every single molecule have 8 electrons? Well, let's count. So remember, how many electrons is in each bond? 2, right? So because you want to think of it as this. That's what you want to think of it as, right? And so because they're sharing that electron, each atom can count 2 for to be part of their octet. So when you look at this 8, right, or the oxygen, we want to have 8 electrons surrounding it. So we have 1, 2, 3, 4, 5, 6, 7, 8, right? That's for just this oxygen. Right? 1, 2, 3, 4, 5, 6, 7, 8. Okay. And so now you basically want to go ahead and look at every single molecule to make sure that it satisfies the octet rule. So now we look at carbon. Okay, I'm going to erase the dots because you don't draw the dots for the lines. I just wanted to remind you that there are two electrons per bond. Okay, so now we go and look at carbon, right? So when we look at carbon, how many electrons are surrounding it? Well, there's only 2 bonds that are connected to it. So you're going to have the 2 electrons here and 2 electrons here. Well, that's only 4, right? So this oxygen has 8. This carbon has 4 valence electrons, and this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So the oxygens are good, right? The oxygens are happy, but the carbon is not happy right now. So what we're going to have to do is basically share more electrons from our oxygens with the carbon, right? But we know that we cannot make more than 3 bonds. So when we share some more of the electrons with carbon, that creates another bond. So you want to kind of think about it like this. So if I have 8 here, I can share these 2, right, with carbon and create a new bond. So I like to kind of draw it like this. So if I made a bond with oxygen up here, right, and I use these 2 molecules or these 2 electrons to make a bond. So now that would give my carbon 1, 2, 3, 4, 5, 6. So really I can do that again, right, on the other oxygen. I can borrow these 2 here. Right? So I can share these 2 electrons from this oxygen and share these 2 electrons with this oxygen for this carbon, and that gives me 8 electrons, because now I have 1, 2, 3, 4, 5, 6, 7, 8. Okay? So let me erase this part. So hopefully you wrote this down. I hope. Okay, so now our final formula will be our final Lewis formula. So that will be the final formula. So the carbon will now have 1, 2, 3, 4, 5, 6, 7, 8 electrons surrounding it. And with the oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8. In this oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8. So our final formula, our Lewis dot structure, is now going to have 2 double bonds of oxygen bonded to the carbon. Okay? So that is how, those are the steps of how you're going to draw out these Lewis dot structures. So let's go back to these tips and tricks. Okay, so these useful tips and tricks. So like I was saying, your arrangement of atoms is usually symmetrical. So like how we have this oxygen, we have these straight across from each other, right? The reason we have them straight across from each other is because it needs to be asymmetrical. And why does it need to be asymmetrical? Well, what are these? These are a whole bunch of electrons, right? There's a whole bunch of electrons here and a whole bunch of electrons here. So we know that opposites attract, likes what? Repel. Exactly. So if these are electrons and these are electrons, they don't want to be near each other whatsoever, right? They're like, OMG, I want you to be on the opposite side of the room from me if possible, because I don't even want you near me. So that's why they're always going to be this symmetrical way, okay? Unless there's like the unshared bonds, then sometimes that will kind of change the orientation. But for the most part, they want to be as far away apart as possible. The central atom tends to be the one that has the least electronegative and is present in the least quantity. So when you look at like carbon dioxide, right? So there's carbon dioxide. So the carbon is probably going to be in the middle because there's 2 oxygens, right? So that's just also a thing. And remember that when you think electronegativity, right, you're going to think E decrease, decrease, right? Electronegativity. Okay. Right? So, if you were to base that off of, or use that, right, without just saying, okay, with this like 4th bullet point, the carbons are often the central atom. So if you were actually to use the electronegativity selection, right, based off of which is the least electronegative, you can always just look at the periodic table, right? So that's something that is like a surefire way of making sure that you know which one is the central atom. So if you don't know, you're like, oh my God, there's a carbon, but there's also another one here. Like, I just don't know. Well, the best thing to do is pull out your best friend, called the periodic table, and ask her how she feels. And look at her his electronegativity trends, right? So when we look at carbon on here, and we look at oxygen, so it's decreasing in this way, so the carbon is further behind the oxygen, right? So that's another reason that you can tell that the carbon is going to be in the center of the formula versus the oxygen. Hydrogen are always terminal atoms. So if you have anything that has hydrogen in it, any type of compound, the hydrogen is always going to be terminal. Why? Because it only has 1 electron, right? So it can't share, it can't have a double bond. It can't have a whole bunch of bonds that it's created to. It can only share with 1 other electron because it's wanting to satisfy the duet rule, which means that once it has 2, it's full, right? Like all the rest of them want 8, but hydrogen only wants 2, hydrogen and helium. So once hydrogen has 2 electrons, which means it can only share one with 1 other electron. So that's why it can only have B terminal. Okay, so, and go off of what I was just saying, use the duet rule for the hydrogen and helium atoms, use the octet rule for the other atoms. All right, let's just keep going. Okay. So now let's just go ahead and go through a couple of these examples. All right. Let's do this. Okay. All right. So let's go ahead and do these examples. So draw the Lewis structures of each of the following molecules. So we have CH4. Oh. Whoops. Okay. Maybe this isn't a good idea. So we have CH4, right? So remember, the first thing that you want to do is write out the skeleton structure, right? So it has carbon, it's CH4, so carbon is going to be the center atom, right? Because it's always generally a center atom. But also we know with hydrogen, it's going to be terminal anyways. And carbon is going to be, it's going to be terminal anyways. So we're going to have 4 bonds with the carbon onto these hydrogens, right? So this is our skeleton structure. The carbon in the center with 4 bonds of hydrogen connected to it. Yep. So now, the next thing that we want to do is we have to calculate the number of valence electrons. So, in order to calculate the number of valence electrons, we have to add up how many valence electrons are here for this whole molecule. So, carbon has 4. And hydrogen has 1, but there's 4 hydrogens, so it's going to be 8. So 4 plus 8 is 12. So we have 12 valence electrons, right? And then the next thing that you're going to do is subtract the number of bonded electrons from the total number of valence electrons. So we're going to do, so when we look at our skeletal structure, well, first, right, we have to say how many bonded. So we look at our skeletal structure. We have 2, 4, 6, 8, right? Because every bond has 2 electrons, 1 from the hydrogen, 1 from the carbon, so on and so forth and the rest of these. So 2, 4, 6, 8. So we have 8 bonded, and we have 12 total valence. Okay? So that means we're going to have 4 unpaired electrons. Is this? I am tripping. It's like, that doesn't make sense. I don't know where I got. That's the one thing about, if you guys were here, you would have corrected me. So this would be, I don't know where I got 8. Or, yeah, okay. So 1 times 4 is not 8. Okay, it is 4. I don't know where I got that from. I guess I was thinking adding this already. So you have a total of 8, right? Or what am I talking about? So yes, so a total of 8 valence electrons total, right? Because we have 4 for carbon when you look at the periodic table, right? So remember, don't forget, and I'm just going to mention this again, you want to go and look at, see, the row that carbon's in, it's in the 4 here, right? So that means it has 4 valence electrons. Hydrogen has 1. So since there's four hydrogens, there's going to be 4 hydrogens, 4 valence electrons plus 4 hydrogen or carbon valence electrons. So you have 8 valence electrons total. So the total number bonded is 8 electrons, and the total number of valence electrons is 8 valence electrons. Okay, this is making more sense. So now, that means you're going to have, you have 8 valence electrons total, and you have 8 bonded, so therefore you have no lone pair. Right? And you can double check by saying, okay, is this hydrogen satisfied? Yes, because it only wants 2. And so on and so forth for the other 3. And then the carbon, is this satisfied? Yes, because it has 2, 4, 6, 8 electrons surrounding it. Right, so you're done. So the answer is just this structure that you drew in the beginning, which is skeletal structure, because it had no lone pair. Okay, so let's do the next one. Okay, so the next one is H2O. All right, so first you want to find the center atom. Well, we know what about hydrogen. It's always going to be at the end because it can only have 2 electrons. So the oxygen is going to be in the middle. So if we were to draw our skeleton structure, right, this is what we would draw. Because we have hydrogen and hydrogen and 1 oxygen, right? So then the second step we want to do is calculate the total number of valence electrons. So for oxygen, there's 6, and then for hydrogen, there is 1. But because there's 2 hydrogen, we're going to multiply that by 2. So we have 6 plus 2, which is 8 valence electrons total. Okay, so hopefully I'm not going too fast. Hopefully you guys can understand that you're calculating this total valence electron number I got from looking at the periodic table, looking at the chart, right? And when you look at the column of where oxygen is, it is in the 6th column. Right? You see that? So that's where I got that 6 from. Okay, so now the next step is you want to write out, here I'll put it over here, the number, or subtract the total number of valence electrons and subtract the bonded number. Right, and this is to get unpaired electrons that you're going to add to your formula. So how many total valence electrons do we have? Well, we have 8 total valence electrons, right? And how many bonded valence electrons do we have? Well, how many electrons are in each bond? 2. So we have 1, 2, 3, 4. So 8 minus 4 is 4 unpaired electrons. Okay? So now I'm going to add this number of unpaired electrons into my compound or my new formula, right, when I write it out. So I have, since first of all, we know, usually, right, you would start with putting your electrons on the ends, like I said. But here, since we know that these are terminal, right, they're already happy, we're going to add our electrons immediately to the center, okay? So, this is how you would think you would want to write them, right? Yes? Well, actually, the way that you would write them, and we'll go over this in the next part of chapter 8, is that you want to write them kind of bent. So they'll be slightly bent in order to accommodate these unpaired electrons. So like remember I was saying that all of these things are electrons and they want to be as far away as possible. So these are like huge, right? Because these are bonded to a whole another atom. So like the electrons here and the electron force is way bigger than these two unpaired electrons. So these aren't going to be as far away as possible, right? They're going to be they're going to be kind of closer to each other. So really, this molecule is going to be it's going to look like this. Okay? And this would be the bent conformation. And we haven't gotten to that point yet where we talk about the actual geometrical structures that each of these take, because there's actually geometrical names that you use in order to say what type of structure this is. And normally we put these little ears, I like to call them ears. They're not necessarily ears. They're kind of just bubbles to kind of help to identify where the lone pair are, if there's like several. So you kind of put, like a little bubble sometimes. I mean, if it's not really obvious. Like these two are really close to each other, so it makes more sense to put them further apart. Okay. Okay. So the next four then that I'm going to do, I'm actually going to wait and I'm going to do them with you tomorrow. So then we can also kind of go over those together if you guys have any questions, if you are still confused as to how to do these problems. I think it'll be a good way for us to kind of do them all together. Alrighty, and I will see you guys tomorrow at 3 p.m. Bye.